Hello, everyone, and welcome to the final installment of our series on multilingual AI in production. My name is Dmitriy, and I'm an AI/ML engineer specializing in NLP and multilingual systems. So, if you've been following this series, you've learned about deployment challenges in webinar 1 and 2. In webinar 1, in webinar 1 we discussed deployment challenges, and in webinar 2 we discussed data pipeline architecture. And today we will be tackling what might be the most practical topic of all, which is optimization. Here's the reality I want to set up front. The best model is not always the right model, because in production you're constantly making trade-offs between accuracy, latency, costs, and maintainability. So today I'll give you a framework for making these decisions systematically, plus concrete techniques you can apply immediately. By the end of this session, you'll have a practical toolkit for optimizing multilingual models without sacrificing the performance that matters for your specific use case. Let's start by understanding why optimization in multilingual AI is fundamentally different from monolingual optimization. In monolingual system, you have one model, one language, and one set of trade-offs. You optimize for a single user population, which is quite simple. But in multilingual systems, optimization becomes multidimensional. You're not just optimizing one accuracy latency curve, you're optimizing n curves simultaneously, one for each language. And here's the kicker: they often move in opposite directions. So let me give you a concrete example. You have a multilingual model serving English, Spanish, and Thai. You apply quantization to reduce latency by 40%. And here's what happens. English accuracy drops by 0.5%, which is very noticeable. Spanish accuracy drops 1.2%, acceptable. And Thai accuracy drops 4.8%, which is kind of a problem. And why is that? Because Thai had less representation in the original training data, and when you compress the model, you're effectively throwing away information. And the model preferentially forgets the pattern it learned least well, which are typically low resource languages. So this is the fundamental challenge. Optimization techniques that work beautifully for high resource languages can devastate low resource language performance. And the solution here is not to avoid optimization at all. It's to optimize intelligently with per language awareness. And that's what we'll learn today. So here's our roadmap for today. First, we'll build a model selection framework, how to systematically compare mBERT, XLMR, and other architectures. When should you fine-tune versus use off-the-shelf ready model? What evaluation criteria matter beyond accuracy? Then we'll dive into optimization techniques like distillation, quantization, pruning, and language-specific approaches. What actually works, what doesn't, and what the papers don't tell you. After that, we'll have real-world trade-offs. I'll share cost-benefit analysis framework, infrastructure implications, and maintenance strategies. Finally, case studies and best practices, concrete examples from production deployments, common mistakes I've seen, and how to future-proof your multilingual systems. And we will finish up with a Q&A session. Before we optimize, we need to select the right base model. This decision constrains everything that follows. Let's look at these decision metrics. On the vertical axis, we have the number of languages you need to support. On the horizontal axis, we have your accuracy requirements. For 1 to 3 languages with high accuracy requirements above 90%, language-specific models are your best bet. Camembert for French, RuBERT for Russian, BERT-based for English. These are trained specifically for the language and consistently outperform multilingual models by 3 to 5%. When you have 3 to 10 languages with moderate to high accuracy requirements, you're in a hybrid territory. Use language-specific models for your top 2 to 3 languages by traffic and a multilingual fallback for the rest. For more than 10 languages, or when accuracy requirements are moderate around 80-85%, a single multilingual model like XLMR is usually the pragmatic choice. The operational complexity of maintaining 10 plus models, it definitely outweighs the accuracy benefits. For all low accuracy requirements below 80%, mbert is often sufficient and gives you better latency and lower cost than XLMR. But here's what this matrix doesn't show. Your specific data matters more than any general rule. I've seen cases where mbert outperformed XLMR on certain domain-specific tasks because the domain data align better with Wikipedia, and that's actually the mbert's training source. And then Common Crawl, which is XLMR's training source. So this framework gives you a starting point, not an answer, and you still need to benchmark on your specific data. Let's do a detailed comparison of the models you're likely to consider. Starting with mbert, it was released in 2018. It's multilingual bird, has 110 million parameters and supports 104 languages. It was trained on Wikipedia data, and its key characteristics are smaller size, which means faster inference at around 30 to 50 milliseconds. And that's on CPU. The tokenizer uses 110,000 vocabulary tokens shared across all languages, and that creates tokenization inefficiency for non-latent scripts. Cross-lingual transfers are quite decent but limited. When to use? Cost-sensitive deployments, latency-critical applications, when your languages are mostly high-resourced European languages. It's also a good choice for prototyping because it's fast to iterate. Then XLM Roberta. It comes in two sizes. The base model has 270 million parameters, and the large one 550 million. It was released in 2019 and trained on 2.5 terabytes of common crawl data across 100 languages. Key characteristics: significantly better cross-lingual transfer than mbert, better handling of low-resource languages due to more diverse training data, and state-of-the-art performance on most multilingual benchmarks. The downside: 2.5 larger than mbert and 2.5 times larger than mbert, and that means 2 to 3 times slower inference. The large model is 5 times larger and may require a GPU for reasonable latency. When to use XLMR? When accuracy is paramount, when you have GPU resources available, when supporting low resource languages where mbert struggles. Then we have language specific models like RuBERT, CommonBERT, BERT, etc. And these models are trained on a single language with a tokenizer optimized for that specific language. Key advantage is 3 to 5% higher accuracy for that specific language, more efficient tokenization, meaning longer effective context, but there is a key disadvantage, which is no cross-lingual capability, so you must maintain multiple models. And when those language-specific models are best used for your highest traffic languages, where that extra 3 to 5% accuracy translates to meaningful business value. And the pattern that could be seen most often in successful deployments is that XLMR base as the workhorse for most languages, then language-specific models for the top 1 to 3 languages by traffic or business importance. Now, a question which comes up quite often: should I fine-tune or just use a model off the shelf? The answer depends on 3 factors. Factor 1: how much labeled data do I have? Look at this learning curve chart. The horizontal axis shows fine-tuning examples from 0 to 10,000, and the vertical axis shows accuracy improvement over zero shot. With 0 examples, you're doing zero shot inference. The model uses only what it learned in pre-training. For tasks that align with pre-training, that like sentiment analysis or NLI, zero shot can be surprisingly good, sometimes 70 to 80%. With 100 to 500 examples, you see the steepest improvement. This is a few shot territory. You can gain 10 to 15% over zero shot. With 1 to 5,000 examples, improvement continues but flattens. and you are in the diminishing return zone. Beyond 10,000 examples, gains are marginal unless your task is very complex. The next factor, how domain specific is your task? General tasks are general tasks like sentiment, topic classification, and similarity work well with minimal fine tuning. Domain specific tasks like medical in ER, legal clause classification, or technical product categorization, these tasks need more fine tuning data because the pre training corpus didn't cover your domain well. Factor 3, how different is your data from the pre training distribution? If your text is clean, well formed prose, off the shelf works better. If your text has domain jargon, typos, mixed languages, or unusual formatting, you need fine tuning to adapt. My rule of thumb is always try zero shot first because it costs nothing and sets your baseline. If zero shot gives you 80 or more percent accuracy, then you might be done. Or if it's below 70%, then you have to plan for fine tuning. So accuracy is the metric that we all obsess over, but actually it's not the only one that matters. Let me show you a more comprehensive evaluation framework. First, per language accuracy breakdown. Overall, 85% accuracy might hide the fact that English is 92% and Thai is 58%. So always break down by language. Set minimum acceptable thresholds by language, not just overall. Second, latency percentiles. Don't just measure average latency, but also measure P50, P95, and P99. Because I've seen some models with great P50 latency at 40 milliseconds, but P99 at 500 milliseconds due to outlier requests and usually long texts or languages with inefficient tokenization. And users experience the P99, not the average. Third, throughput under load. Test with realistic concurrent request patterns. Some models degrade gracefully under load, others fall off a cliff. Know which type you have. Fourth, memory footprint. This determines your infrastructure costs and scaling characteristics. A model that fits in a 4 gigabytes of RAM can run on smaller, cheaper instances than one requiring 16 gigabytes, especially with current RAM prices. Fifth, cold start time. If you're using serverless or auto scaling, how long does the model take to load? For example, XLM large can take 30 or even more seconds to load from disk, and that's quite a long time for the first user after scale up event. 6. Calibration. Is the model's confidence well calibrated? A model that says 90% confidence should be right 90% of the time. Poorly calibrated models are quite dangerous because you can't trust their confidence scores for downstream decisions. And here's the framework you can use. Create a scorecard with weights for each criterion based on your business needs: latency critical application, weight latency heavily, customer facing with diverse users, weight per language accuracy heavily. Run every model candidate through the same scorecard. And before we dive into optimization techniques, let me pose a scenario for you guys to think about. You are deploying a customer support classification model. You support English with 70% of traffic, Spanish with 20%, and 5 other languages sharing the remaining 10%. Your current XLM-R large model achieves 91% overall accuracy but has 180 milliseconds latency, which is above your 100 milliseconds target. So here are 3 options you have. Option A, quantize the model. Expected outcome, latency drops to 90 milliseconds, accuracy drops to 89% overall, but time drops from 78 to 71. Then the second option B, you could switch to Embed. Expected outcome, latency is 45 milliseconds, accuracy is 84% overall, Thai is 68%. Then the third option C is use a hybrid approach with distilled XLM-R for English and Spanish and Embed for everything else. Expected outcome: latency is 60 milliseconds average, accuracy is 88% overall, tie stays at 72%. So think about which one you choose and why, and we'll come back to this later after I cover the techniques, and you'll have better intuition for the trade-offs. Now let's dive into optimization techniques, starting with knowledge distillation, which is actually my favorite technique for multilingual optimization. So the concept is simple here. We train a smaller student model to mimic a larger teacher model. The student learns not just the correct labels, but the teacher's confidence distribution across all classes. This transfers more information than hard labels alone. And why is this particularly powerful for multilingual? Well, because the teacher model, let's say XLM large, has learned rich cross-lingual representations. And through distillation, some of this knowledge transfers to the student, which even if the student has fewer parameters. So here's a typical distillation setup. The teacher is XLM large with 550 million parameters. The student is a smaller architecture. This could be, let's say, DistillBird. Multilingual with 66 million parameters, or even a custom architecture. So training uses soft labels from the teacher with temperature scanning. And just look at these results from a distillation experiment on sentiment classification. Teacher XLM large, 91.2% accuracy, 180 milliseconds latency on CPU, and 2.2 gigabytes model size. Student distillbird, 87.8% accuracy, 55 millisecond latency, 0.5 half gigabyte of model size. And student custom 4-layer model, 85.1% accuracy, 35 millisecond latency, and 1/4 of a gigabyte model size. So the 4-layer student achieves 93% of the teacher's accuracy with 5 times lower latency and 9 times smaller size, and that's quite a massive win. But here's the critical insight for multilingual. Distillation quality varies by language, and in the same experiment, English retained 98% of teacher performance, Spanish retained 96, Russian retained 91, and Thai retained 84. So the student learns high resource languages better, which is expected, and if Thai performance is critical, you may need a larger student or language-specific distillation. Language-specific distillation is an advanced technique where you distill separate students for different language families and then ensemble or route. This can recover much of the low resource language performance, but adds, well, with several models, it adds operational complexity. Now let me walk you through the practical implementation of multilingual distillation. The key hyperparameters are temperature, typically set between 2 and 5. Higher temperature makes the teacher's probability distribution softer, which transfers more information but can make training noisier. Start with 4 and adjust based on validation performance. Then alpha, or the weight of distillation loss versus hard label loss. It is typically between 0.5 and 0.9. Pure distillation with alpha equals 1 sometimes works, but mixing in some hard labels loss usually helps. Start with 0.7. And student architecture matters more than you think. A 4-layer bird-like architecture is a good starting point. Going below 3 layers typically causes catastrophic accuracy loss for complex tasks. Width, which is a hidden size, can be reduced more aggressively than depth. The loss function combines soft target cross entropy and hard target cross entropy, weighted by alpha and 1 minus alpha respectively. Here is one critical tip though. Use language stratified sampling during distillation. So if your training data is 60% English and 5% Thai, the student will learn English well and Thai poorly. Sample to give each language roughly equal representation during distillation training, regardless of your production traffic distribution, and you can always calibrate later. So training typically converges in 3 to 5 epochs for classification tasks. Uh, so don't overtrain. The student can start to overfit to teacher quirks rather than learning generalizable patterns. So now for quantization. Quantization reduces model size by using lower precision numbers. Instead of 32-bit floating point weights, you use 8-bit integers. The model gets 4 times smaller and inference gets 2 to 3 times faster. And there are two main approaches. You have post-training quantization, or PTQ for short. It is the easier approach. You take a trained model, convert weights into int 8, and you're done. No retraining needed, and with tools like ONNX runtime and TensorRT, they make this nearly plug and play. The results are typical 0.5 to 2% accuracy drop, 2 to 4 times speed up, and 4 times model size reduction. Then you have quantization aware training, or QAT, and it is more involved. You simulate quantization during training, so the model learns to be robust to low precision weights. This requires retraining but gives better accuracy. The results are typical. For results, it is typical to have 0.2 to 0.5% accuracy drop, same speed up, and size benefits as PTQ. Now here is the multilingual caveat. Quantization disproportionately impacts low resource languages. So look at this accuracy retention chart after PTQ quantization. English retains 99.5% of original accuracy, Spanish 99%, Russian retains 97.5%, and Thai 94.2%, and Korean 93.8%. So the pattern here is clear. Languages with less training data are more sensitive to quantization. Their learned patterns are encoded in more fragile ways that don't survive precision reduction. And if you're quantizing and have important low resource languages, so consider using QAT instead of PTQ. Also using higher precision, for example, int 8 instead of int 4 for critical layers, and separate quantized models per language group. For example, quantize aggressively for English and lighter touch for Thai. Also, one more thing, always measure quantized accuracy on your actual data and not benchmarks, because quantization effects can vary significantly by task and domain. Pruning removes unnecessary weights from the model. So the idea is that many weights contribute little to prediction and can be zeroed out. And there are two main types. Unstructured pruning zeroes out individual weights based on magnitude. So you might remove 30 to 50% of weights while retaining 95% accuracy, or even more than 95%. So the problem is sparse matrices are hard to accelerate without specialized hardware. So you get smaller models, but not necessarily faster inference on standard hardware. Structured pruning removes entire structures like attention heads, layers, or hidden dimensions. This creates smaller, dense models that accelerate on any hardware. It's more aggressive and typically causes more accuracy loss, but the speedup is real. For multilingual models, head pruning is particularly interesting because research shows that different attention heads specialize in different linguistic phenomena. Some heads focus on syntax, others on semantics, others on cross-lingual alignment. And here is a finding from multilingual head analysis. In XLMR, certain attention heads are critical for specific languages. Pruning head 7 in layer 5 might have minimal impact on English, but catastrophic impact on Japanese, because that head learns something specifically important for Japanese syntax. The implication is that naive pruning that removes the same heads across all languages will disproportionately harm some languages. Language-aware pruning, where you identify which heads matter for which languages and prune accordingly, is more complex but preserves multilingual capability better. For most production use cases, though, I would recommend starting with distillation over pruning, because distillation is better understood, more predictable, and easier to implement correctly. and only use pruning when you've exhausted distillation gains and need further optimization. So, sometimes the best optimization is not to use a multilingual model at all. Let me explain. When language specific optimization makes sense is uh, in these scenarios. The core trade off: multilingual models are convenient because one model serves all, but compromise they are not optimal for any single language. Language-specific models are optimal for the language, but require N models for N languages. And here's a decision framework. If a language represents more than 30% of your traffic, consider a dedicated language-specific model. The accuracy gains justify the operational overhead. If a language represents 10 to 30% of traffic, run an experiment. Measure the accuracy delta between your multilingual model and language-specific model on your actual data. If the gap is more than 3%, consider the dedicated model. If a language represents less than 10% of traffic, stick with the multilingual model unless accuracy requirements are unusually high for your specific task. But there is an even smarter approach that maintain completely separate models: adapter modules. Adapters are small trainable modules inserted into a frozen pre-trained model. So you train language-specific adapters that specialize the multilingual model for each language. The base model is shared, only the small adapter layers differ. The benefits are that you get much of the accuracy benefit of language-specific models with dramatically lower overhead. The adapter for each language might be only 2 to 5% of total model parameters. You can even stack adapters for language plus task specialization. The implementation is you use the adapters library, adapter transformers. It works with standard Hugging Face models, and training adapters require much less data than the fine-tuning. Often 1 to 5,000 examples per language is sufficient. And here, well, some results from my experiments. Language-specific adapters recover 60 to 80% of the gap between multilingual and dedicated language-specific models, and that's all at a fraction of the cost. Now let me summarize the optimization techniques with the comparison table. Knowledge distillation. Latency reduction is 2 to 4 times accuracy impacts, is typically 2 to 5% drop. Implementation complexity is medium, and it works best when you need significant model size reduction while preserving accuracy across languages. Then you have post-training quantization. Latency reduction is 2 to 3 times. Accuracy impact is 0.5 to 2% drop, but high for low resource languages, and implementation complexity is low. It works best for quick wins when accuracy margins allow. Then we have quantization aware training. Here latency reduction is 2 to 3 times. Accuracy impact is 0.2 to 0.5% drop. Implementation complexity is medium to high. It works best when you need quantization benefits with minimal accuracy loss. Then we have structured pruning. Latency reduction is 1.5 to 2 times. Accuracy impact is 1 to 3% drop. Implementation complexity is quite high. Works best when combined with distillation for maximum compression. And then we have language-specific adapters. Latency impact is minimal, which is a slight increase. Accuracy impact is positive with 2 to 5% improvement per language. Implementation complexity is medium, and it works best for high traffic languages where accuracy matters most. So my recommended approach for most teams would be start with post-training quantization. It's nearly free and gives immediate wins. If you need more, add distillation with a student model sized for your latency budget. For your top 2 to 3 to your top 2 or 3 languages by business importance, add language-specific adapters. And this layered approach gets you about 80% of possible optimization benefit with just 20% of the complexity. Now let's talk money. Every optimization decision is ultimately a business decision at the end of the day. Here's a framework for quantifying trade-offs. Let's start by calculating current costs. Consider infrastructure costs. What instances are you running? How many? What's your monthly bill? Then calculate a cost per prediction. If you spend $5,000 per month and serve 10 million predictions, that's 0.0005 dollars per prediction. Now calculate the cost of errors. This is harder, but it's critical. If your model misclassifies a customer support ticket, then what happens? Maybe the ticket goes to the wrong queue, adding 30 minutes to resolution time. And if your support costs $50 per hour, that's 25% per error. At 85% accuracy, you have 15% errors. On 10 million predictions, that's 1.5 million errors, costing 37.5 million in downstream impact. Of course, this is a simplified example, but it illustrates the point. The cost of accuracy loss often dramatically exceeds infrastructure costs. Now let's model optimization scenarios. Let's talk about model optimization scenarios. Scenario A, quantize to save infrastructure costs. Infrastructure drops from $5,000 to $2,000 per month, which is 60% savings and $36,000 per year. Accuracy drops from 85% to 83%, which is 2% more errors. 200,000 additional errors per month times $25 equals $5 million of additional downstream cost per month. So the math here is brutal. You saved $3,000 per month, but created a $5 million sinkhole in downstream costs. And this is why optimizing purely for infrastructure costs is usually wrong. Then we have scenario B, distill to balance. Infrastructure drops to $3,000 per month. Accuracy drops from 85% to 84%. 1% more errors. 100,000 additional errors times 25 equals 2.5 million additional cost. Still not great, but better. You need to find the accuracy level where the marginal cost of error equal the marginal infrastructure savings. The key insight here is know your error costs. Without this number, you're optimizing blind. Work with your business stakeholders to quantify what errors actually costs, then make data-driven optimization decisions. Now let's make this multilingual specific. Error costs aren't uniform across languages. Consider this scenario with two languages. English 70% of traffic, 92% accuracy, with average transaction value of $100. Thai 50% of 5% of traffic, 78% accuracy, average transaction value to $200. English error rate in this example scenario is 8%. Thai is 22%, but Thai transactions are worth 2 times more. And if you optimize in a way that drops English accuracy by 1% and Thai accuracy by 5%, English 1% of for English 1% more errors on 70% of traffic is 0.7% more errors overall, each costing roughly $100. Thai 5% more errors on 5% of traffic equals 0.25% more errors overall, but each costing roughly $200. So the Thai accuracy drop has a disproportionate business impact relative to its traffic share. That's why per language accuracy monitoring matters, and it's why your optimization strategy should be language aware. Here's a practical framework though. For each language, calculate traffic share multiplied by 1 minus accuracy multiplied by error cost. This gives you error weighted cost per language. Then optimize to minimize total error weighted cost, not just overall accuracy, because sometimes this means accepting worse accuracy in English where you have margin to preserve accuracy in a high value, lower volume language. Create a dashboard showing error weighted cost per language, and when evaluating optimizations, show the impact on this metric, not just accuracy. Now let's talk about how optimization choices affect your infrastructure architecture. Model size determines instance type. Embed at 0.5 gigabytes runs comfortably on T3 medium with 4 gigabytes of RAM. XLMR base at 1.5 gigabytes needs T3 large with 8 gigabytes, and these are AWS instances, by the way. Then we have XLM Arch at 2.2 gigabytes, and it needs T3 X large or GPU instances for reasonable latency. But quantized models change this equation. Quantized XLM base drops to about 0.3 gigabytes running on smaller instances, and this isn't just a cost saving, it's an architecture change. Smaller instances scale out more granularly, handle failure better, and have lower cold start times. You can consider this auto scaling. Yeah, let's just consider this auto scaling comparison. Non-quantized XLM large on G4DN X large instance cost is $0.5 to $6 per hour. Cold start is around 45 seconds because we have to load 2.2 gigabyte model. Minimum scale is 2 instances for redundancy, so minimum cost is $767 per month. For quantized XLM base on T3 medium, instance cost is $0.042 per hour. Cold start is around 8 seconds. Minimum scale is 3 instances because smaller instances warrant more redundancy. And minimum cost is $91 per month. And that's an 8 times reduction in minimum cost from quantization alone. But there is a catch. Of course, there is a catch. If quantization drops your tie accuracy below acceptable levels, you might need a separate non-quantized model path for tie. And now you have 2 models to deploy, monitor, and maintain. The infrastructure stability benefit partially evaporates here. And this is why I recommend modeling your complete infrastructure costs at different optimization levels before committing to one solution. Include the complexity cost of multi-model deployments in your analysis. That's quite important. Now let's talk about maintaining optimized models. Optimized models require different maintenance strategies than baseline models. Let me share what I've learned. First challenge, retraining drift. Your baseline model was trained on data from 6 months ago. You've since collected new data, fixed label errors, and added new categories. When you retrain, the accuracy landscape shifts. Your carefully tuned quantization might now cause different degradation patterns. Solution include optimization in your retraining pipeline. Don't just retrain the teacher model, retrain the student, requantize, and reevaluate, and automate this. Challenge number 2, language drift. New slang emerges, terminology changes, user behavior shifts, and these shifts affect languages differently. For example, your Thai users might start code switching more with English terms, causing your carefully optimized Thai performance to degrade faster than English. Solution is pro-language monitoring with alerting on accuracy degradation. When a specific language drops below threshold, trigger investigation and potential retraining. Third challenge, cascading optimization. If you've done distillation plus quantization plus pruning, each layer depends on the previous one. Retraining the teacher means redistilling the student, means requantizing, means repruning, and this is a lot of work. Solution is document your optimization pipeline as code. Use ML pipelines tools like MLflow, Kubeflow, or even a well-structured makefile. Make regenerating the optimized model a single command. And fourth challenge is A/B testing optimized models. When you deploy a new optimized version, you need to A/B test, but optimized models might have might behave differently under load than in offline evaluation. Solution here is shadow mode deployment. Run the new optimized model alongside production, comparing predictions on live traffic without serving them. Once you validate performance matches of fine metrics, do a proper A/B test. Let me walk through a real optimization case study from an e-commerce product classification system. The starting point is XLM large model serving 8 languages, accuracy 89% overall, latency was 180 milliseconds on CPU, violating the 100 milliseconds SLA, and monthly infrastructure costs was 12,000. The business constraints. Latency must be under 100 milliseconds. Accuracy must stay above 85% overall. Russian accuracy must stay about 80% because it was a key market despite being only 15% of traffic. Here's the optimization's journey. Attempt 1. Post-training quantization results. Latency dropped to 110 milliseconds. Accuracy dropped to 87.5% overall, but Russian dropped from 84 to 76%, which violated the constraint. So this attempt was rejected. Attempt number 2. Knowledge distillation to a 4-layer student. Results: latency was 65 milliseconds. Overall accuracy was 86.2. Russian was 79%. Close, but still below threshold. Rejected. Attempt 3. Knowledge distillation plus Russian adapter. Results: latency was 68 milliseconds, slight overhead from adapter. Overall accuracy was 86%, Russian was 82.5%, and this met all constraints. So final architecture: distilled 4-layer model as base. Russian adapter activated for Russian traffic, detected via language detection. English adapter for English traffic, further 2% accuracy boost. Other languages use base distilled model without adapter. And final results: latency was 68 milliseconds, which is 62% improvement. Overall accuracy was 86.8, which is within acceptable range. Russian accuracy was 82.5%, which exceeded the requirement, and infrastructure costs dropped to $4.5 thousand per month, which is 62% in savings. And the key insight here is a single optimization technique wasn't enough. The combination of distillation for latency plus language-specific adapters for critical accuracy requirements altogether achieved the goal. Now let me share the optimization mistakes that can happen most often, in my opinion. Mistake 1. Optimizing on benchmarks instead of production data. XLM R quantized might show 0.5% accuracy drop on XNLI benchmark, but 3% drop on your specific e-commerce data because your data has different characteristics. So always evaluate on your production data distribution. Mistake number 2. Ignoring per language impact. Overall accuracy dropped 1%. This might mean English dropped 0.2% and Thai dropped 8%. If Thai is critical market, you've made a terrible mistake that's hidden in aggregate metrics. Mistake 3. Optimizing too early. If your model accuracy is 75%, optimization should not be your priority. Improve the baseline first. Optimization is for squeezing efficiency out of already good models, not for fixing fundamentally underperforming ones. Mistake number 4. Not accounting for load patterns. Your model might perform great at P50 latency, but terribly at P99 when the system is under load. Test with realistic load patterns before declaring optimization success. 5th mistake: forgetting cold start. Serverless and autoscaling are common patterns. If your optimized model takes 30 seconds to load, your users will experience painful delays after scale-up events. Optimize model loading times too. Mistake 6. One-time optimization. Models drift, data changes, requirements evolve. Optimization isn't a one-time event because it's an ongoing practice. Build optimization into your ML ops pipeline. And last but not least, mistake number 7, ignoring the complexity cost. A system with 5 different model variants, conditional routing, and multiple adapter models is harder to debug, monitor, and maintain. Sometimes a simpler, slightly less optimal solution is better overall. So future-proofing. The multilingual NLP landscape evolves rapidly, and how do you optimize today without creating technical debt for tomorrow? Principle 1. Modular architecture. Separate your model serving from your business logic. Use a model serving layer like Torch Serve, Triton, or a simple fast API wrapper that exposes a standard interface. When better models emerge, you can swap them without touching application code. Principle 2. Language agnostic interfaces. Your application should request classify this text, not run XLMR inference. The routing decision on which model handles which language should be encapsulated in your ML service. This lets you optimize routing independently of application changes. Third principle, comprehensive logging. Log inputs, outputs, latencies, and confidence scores per request. When you want to evaluate a new optimization, you can replay historical traffic. When debugging production issues, you have the data you need. Fourth principle, gradual rollout capability. Build feature flags or traffic splitting into your architecture from day one. You'll need it for every optimization experiment. Fifth principle, monitor for when to re-optimize. Set up alerts for latency creep, which is model or infrastructure degradation, accuracy drift, which is data distribution shift, cost anomalies, for example, traffic pattern changes, and these tell you when your optimization is no longer optimal, and you might need to reevaluate your solution. So the models will change, Ember to XLMR to whatever comes next. The techniques will evolve, but a well-architectured system can absorb these changes without massive rewrites. Let's quickly go through the production optimization checklist. Pre-optimization, have you established baseline accuracy per language on production data? Have you measured baseline latency at P50, P95, P99? Have you calculated your error cost per language? Have you defined minimum acceptable accuracy thresholds per language? Optimization selection. Have you tried the simplest optimization first, which is post-training quantization? Have you evaluated per language impact, not just overall? Have you tested under realistic load conditions? Have you measured cold start time? Deployment. Have you set up shadow mode testing before full deployment? Have you configured per test language monitoring? Have you planned A/B tests with proper certification? Have you documented the rollback procedure? And of course, don't forget about the maintenance phase as well. So let me wrap up with the 6 most important lessons from today. First, best model is not always the right model. Optimization is about finding the right balance of accuracy, latency, costs, and complexity for your specific situation. There is no universally optimal configuration. Second one, multilingual optimization requires per language thinking. Techniques that work for English may harm low resource languages. Always measure and monitor per language impact. That's important. Third, start simple, layer complexity. Begin with post-training quantization, add distillation if needed. Add adapters for critical languages. Don't jump to complex solutions before exhausting simple ones. Fourth, know your error costs. Without understanding what errors actually cost your business, you can't make informed optimization trade-offs. Work with stakeholders to quantify this. Fifth, optimization is continuous. Models drift, data changes, requirements evolve. Build optimization into your ML ops practice, not as a one-time project. 6. Architecture enables optimization. A modular, well-instrumented system can absorb optimization changes gracefully. Invest in architecture before optimizing specific models. Multilingual optimization is challenging, but the payoff is real. Serving diverse global users efficiently and cost-effectively. The techniques I've shared today should help you get there. And now time for some questions. Okay, we have our first question. Um, how do you convince stakeholders that a 2 to 3% accuracy job is acceptable? Because they always focus on that number. Uh, oh yeah, I feel this question. So the trick, the trick is reframing the conversation from accuracy aspect to business impact. You don't say just accuracy drops 2%. You say we'll have 200 more errors per month, which costs us X dollars, but we save Y dollars on infrastructure and Z milliseconds on user experience. So make it concrete. You can show that 2% accuracy drop costs 10K dollars but saves 50K dollars. And suddenly that's not about accuracy anymore. That's just about ROI. And honestly, sometimes when you do this math, you realize that accuracy drop actually isn't acceptable, and that's all right too, because that's a valuable finding. Because the point is to make it a business decision, not a technical one. So stakeholders, they understand money and customer impact way better than just some random abstract accuracy percentages. For a team just starting with multilingual, would you recommend starting with mbird or xlmr? Um, well, it depends on your constraints, but if I had to pick one, I'd probably say start with xlmr base, not the large one, but the base version. And uh, I think, yeah, I think go with XLMR base because Mbird is faster and cheaper on one hand, but XLMR base isn't that much slower, and it handles low resource languages way better. So if you start with Mbird and later realize that your Thai or Vietnamese accuracy is terrible, then you'll have to switch anyway. And XLMR base is kind of the sweet spot, the sweet spot uh, because it has good accuracy, reasonable latency, and you have room to optimize it if needed. And you can also always quantize it or distill it later. So starting with mbirds and trying to improve accuracy is harder than starting with xlmr and optimizing for speed. But again, you have to benchmark on your data, and xlmr base just a good starting point. uh, Another question. Um, I have for distillation, do you distill on the same data used for fine tuning, or do you need a separate? Do you need separate data? Uh, good question. So ideally, you want to use the same data distribution as your fine tuning, but you don't necessarily need the labels. So the student is learning from the teacher's outputs, not the ground truth labels. And in practice, I usually just reuse my fine tuning data set, and yeah, that's usually already representative of your task. But there's one thing that if your fine tuning set is small, like under 10,000 examples, you then might want to augment it or add some unlabeled data from your domain. Um, because the more examples the student sees the teacher process, the better it learns. But don't overthink it too much. Just start with your existing data and see how it goes. what the realistic timeline for implementing these optimizations? Like if we have a working model already, okay, um, have a working model already, okay, so rough estimate, I would say, um, well, quantization you can do in a day or two, because it's mostly just export, quantize, benchmark, low effort, quick win. For distillation, it's more like 1 to 2 weeks, if you haven't done it before, like if it's your first time, because setting up the training loop, experimenting with hyperparameters, relating per language, that all takes some iteration, and then adding adapters maybe another week on top of that. So end to end, all those methods, if you're doing like the full optimization stack, quantization, distillation, adapters for key languages, then I'd budget about a month for a first pass, because yeah, and that includes testing and validation. And well, you can do it faster if you cut corners, but yeah, try not to cut corners, especially the first pass. And don't forget about the evaluation part, because you can get some surprises there. Um, what is your go-to tool for quantization on the next runtime or something else? Yeah, on the next runtime is my default, honestly, but yeah, I know it just it works. It's well documented, and one good thing is it's vendor neutral, so you're not locked into NVIDIA or anything. So yeah, the workflow is pretty simple. You just export your PyTorch model to ONNX, then use their quantization tools, and that may take like maybe an hour to set up the first time. But but if you already have some NVIDIA GPUs and you want to squeeze like every last millisecond, then you should probably go with Tensor RT, because it will give you better performance on NVIDIA hardware. It's more complex to set up, and you're tied to NVIDIA, as I said. So yeah, for most teams, I would say ONNX is the right starting point. Uh, but if you, as I said, if you need like to squeeze every last millisecond, you can always move to Tensor RT later if you feel the need to. Do we have any more questions? Okay, I think we have one more question. How to handle the language detection step? Is that another model or rule based? Um, Good question. This one sometimes can be overlooked, because there are a few options. I think I've covered part of that question in the last webinar, but let me go through again. So you have a few options, as I said. Fast text, it has a language detection model that's very minuscule, tiny, and super fast, like sub millisecond, and that's what I use most of the time. It handles 170, I think, languages, and it's honestly good enough for 95% of cases. There's also LangDetect library in Python, which is fine for prototyping, but a bit slower. So for production, fast text is the way to go. Um, just there's one thing is that short texts are quite tricky, because if someone types three words, language detection can be quite unreliable. So you might want a fallback strategy for that, like defaulting to your highest traffic language or using the user's local setting if you have access to that data. Yeah, I think that should answer your question. Okay, I think we're done with the questions. So thank you all for joining the complete series on multilingual AI in production. We've covered deployment challenges, data pipelines, and now optimization. So together, this give you a comprehensive framework for building and operating multilingual NLP systems. You can see my contact information on the screen, and feel free to connect if you have follow-up questions, or just feel free to connect. And yeah, thank you for your attention and good luck with your multilingual deployments.